July, but we're excited to have you. So it's a quick 1 hour call today. We have a lot to fit in, including some updates from the applications program, updates from Jeremy Wardell, our project scientist, and then 3 updates from our PACE science and applications team. And of course, we have another networking break so that we can make sure that you're all saying hi to each other and getting to know each other as well. So just briefly, a couple of updates from the PACE applications program. We had 3 exciting activities happen since we all spoke last. The first is we had an air quality focus session, air quality and applied atmospheric sciences. If you were not able to join in, the link is posted. You'll see this on the slides later, but it's available on our events page. All of the recordings, the presentations, we had a really great breakout activity. So I encourage you, if you are at all interested in this application area and weren't able to join, or even if you just missed a piece of it, please feel free to go back and listen to the event because it was great. We also released our first issue of our newsletter. You may have received that via multiple avenues, so apologies if you have 5 copies of it, but we're happy, we're excited to have shared that. If you didn't get it and want it, it's also available online. And then lastly, we had a listening session with a new community that we're starting to do some outreach with, and that's the Indigenous community. So ITEP is a really fantastic organization based out of the University of Arizona, and we're starting a conversation with them to see from the Indigenous and tribal perspective, can PACE contribute to work that's ongoing in tribal communities. So more to come on that as those conversations continue. So this is something else you've probably heard of, but we're gearing up for our next applications workshop this September. So there's a QR code. We encourage you, if you haven't registered, please register. It's going to be another great event all about PACE science, about PACE applications. Our theme for this year is thinking about how to get PACE applications even farther along in their readiness. So a lot of conversations about data accessibility, about mission synergies, and about co-production and community engagement, in addition to all of the exciting PACE science that happens. So please register and please share that with your networks as well. There's a few other exciting events that are related to PACE, related to our community. So a lot of links are available on this page. There's an RSET training that some of you may find relevant. The Apollo conference registration is closed, but we announced this at our last event, so hopefully some of you are able to sign up if it's something that you're interested in with polarimetric data. We also know that the NASA Earth Science Applications Week is happening. That is, it's a week-long event of applications across all of Earth sciences, so not just PACE, but lots of other missions ongoing and pre-launch missions as well. There's also a Glimmer applications workshop that's actually kind of happening alongside our PACE applications workshop. So that'll be the Friday after our event. We're going to talk about a lot of synergies with Glimmer and other related missions during our workshop, and then we'll have an event that's just focused on Glimmer on Friday, September 16th, I believe. So please register for that if you haven't seen that. Ocean Optics is coming up. Many of you are involved in Ocean Optics. And then, of course, we have additional community of practice telecons. The October telecon is TBD for the moment. It's right after Ocean Optics, and we know a lot of folks will be tired. So we're going to play by ear whether that one will happen or not. But we already have some exciting presentations to come for our January telecon. So keep that placeholder in your calendar, and we'll hopefully, if we don't see you in October, we'll see you in January. So just a quick 10-minute opportunity to say hello. We are going to use thematic areas to break all of you up for just a few minutes, just 10 minutes. And we just, again, we want you to get to know each other, and we want you to maybe talk amongst your groups about why PACE. Why are you interested in PACE? What is it contributing to your work that maybe some other data sets or sensors cannot? So Erin is going to help set up our breakout sessions, and we have 10 minutes to just say hello to each other. It's not meant to be gigantic conversations or anything. Feel free to put your name and email in the chat. We just want to offer a brief opportunity for everybody with every community of practice telecon, a brief opportunity to just say hello and hopefully meet some new faces. Hi, everybody. Welcome back. It looks like we're all getting thrown back into the main room. I hope that's just a quick, enjoyable 10 minutes. I know it's fast and, again, not meant to be having in-depth conversations. If you have ideas for other ways that we can split up the group, I know there were 30 plus folks in the water group, for example. Shoot us an email or just put it in the chat. We'd love to continue to offer just quick, again, opportunities to say hi to each other, but we can organize them in different ways. So if you have ideas, feel free to share. But thanks for being good sports and chatting with each other. So I'd like to pass the floor now to Jeremy. And Jeremy, just tell me when to move along and I'll draw the slides for you.
I serve at your pleasure, Natasha, anytime you want. Oh, go ahead and forward to the next. There we go. Okay. Welcome, everybody. Thanks for coming back to, I guess, our second official community of practice Telecon. It's been a quick couple of months since we caught up in April. So I thought I'd start with a reminder of where we are in the mission. Right now, we are 18 months from launch, so everything is creeping up pretty darn fast. As you can see in the red circle there, this continues to place us in the middle of integration and testing, or INT. And particularly at Goddard, been focusing on the ocean color instrument and the spacecraft activities related to this. We are nearing the end of what we call Phase C. And as you can see in the green box up that says Phase C, what that really means is that our flight builds are nearing completion. And I'll show you some pictures of that later. So what that means to you all is our designs are closed, our instruments are built. You're going to have a spacecraft, 3 instruments all ready to be integrated into one package. That'll be what happens for the better part of 2023. So the rubber has met the road and we are getting to actually start thinking about flying this thing. So next slide then. Yeah, I have like 2 slides of just bulleted updates on everything that's been going on. But the bottom line, just to jump to the real punchline here, is that everything's been going very, very well. It's an exciting time for the project. So next, with regard to the spacecraft, there has been all kinds of work being done, putting various widgets, so forth, onto the spacecraft. As you've seen in previous pictures that I've shown, it's a big cube, but now there's a bunch of other things hanging off of it, like star trackers, GPS receivers, batteries, and even an instrument. So the focus lately has been all of the mechanical and electrical integration of the parts that we need. Most recently, if you care about such things, it's been the flight transmitter and the K band system. A lot of work with reaction wheel assemblies. Generally speaking, most of the parts are there now, and they are awaiting final delivery of just a couple of these things, inclusive of delivery of OCI and the tilt mechanism, which will be a big job that'll take a bunch of months in the fall winter here. Saving the best for last, the really most exciting part is it's not so much a spacecraft anymore, it is an observatory because there's an instrument that has been mechanically and electrically integrated. Specs 1 is the first one that made it. The team from the Netherlands spent the better part of June here, and now our first instrument is actually bolted onto the spacecraft, and data is flowing, everything's talking to each other, which is pretty freaking cool. In other news with OCI, what's also exciting is that it is fully integrated. And what I mean by that is it is finally a complete package. And I'll show you a video of that in a little bit. But the instrument is done. It's still being tested, but it is done. The solar calibrations assembly, the square pulse calibration assembly, the big Earth shield, all attached. It looks like it is going to look. As far as testing goes, they finished EMI testing, which is electromagnetic interference testing. Right now, the conversations are focusing on all the technical readiness reviews for mating the full instrument with the tilt system, after which it will go into thermal vacuum and spend 2 months there doing all of the tests related to operation in a space-like environment. Next slide. Skipping to HARP 2, since basically Specs 1 is done. The rebuild of the flight instrument is continuing. It is going pretty well. Prisms are being bonded to detectors and so forth. The engineering test unit has undergone vibration testing, so we're confident that the anomaly won't repeat itself. The final environmental test campaign was going to be planned for August, so the instrument will be fully rebuilt. It will be sent to Goddard Space Flight Center. It will undergo testing with anticipated delivery to the spacecraft in October of this year. Next. Okay. And then as far as science updates go, just a couple of things in case you are interested. The science team and the science data segment are faithfully working on what we're calling day in the life testing. What this means to you is it's verification of our entire process of pulling science data from the cloud, housekeeping telemetry from S-band transmitter, which is going to ground instead of the cloud, putting all of those packets together, creating science data products, and putting them online. The goal for the end of the year is to make sure we can do that for an entire day of orbits. And next year, we're going to stress the system and try to do this repeatedly for months or so of orbits at a time, with the longer vision that if we know everything is working, once we get to first light, then there shouldn't be too many hiccups, knock on wood, related to having data on the street as fast as possible. As I alluded to quickly earlier, comprehensive performance testing with Specs 1 is underway, and we've confirmed that the science data segment can actually talk to the instrument, which is great. For those of you interested in simulated data, version 8 of our OCA PyToast, which is level 1B Radiance products, has been processed. There's a number of upgrades that are just being verified there, but the general idea is to have improved some of the models that went into that. So check back routinely to the website that hosts these pages. Um, Go under data products on the main PACE website, and you should be able to find it and see what you think about all of it. We're still planning post-launch airborne experiment we're calling PACE Packs. That's underway and making progress. That will be an aircraft campaign off the west coast of the US, roughly 6 months after launch, September of 2024. And then if you are interested in proposing to be part of the PACE validation science team, that will be a late 2022 amendment to Roses 22. So just follow along in Inspires and Roses for the next couple of months, and you'll learn more about that. I will probably have something more meaningful to say in that regard when we meet again in October. Okay, we're going to go to the next slide, and it's a video. I'm going to be quiet. You can start at any time you want, Natasha. It's 4.5 minutes long. I'm actually just going to try to sit quietly because it is pretty fascinating to see this time lapse of 1 year of OCI being developed. So it runs from April 2021 all the way to April 2022, but it can describe far better than I can what the process has been like to come out of a pandemic and build this really kick-ass instrument. Um, you're the first group of people to have seen this. It will be posted on the Paste website, but it hasn't been shown to everybody. So one of the nice things about joining these telecons. And with that, I will actually shut up. Aaron, they showed this or a version of this at our pre-environmental review for our OCI, and they did have music, and it was Johnny Cash's one piece at a time or one part at a time, and it was pretty fantastic. But as you might imagine, that is not possible with some copyright things for public distribution. So OM is the optical module. So what you were looking at before is one of the clean rooms with preparations to go into thermal vac, but it was mostly just the mechanical structure. These are the optics you all care about. So the bottom half of that black canister is the rotating telescope assembly. So that'll be spinning at 6 hertz. That's the structure that you saw before. Well, actually, that's government supplied equipment or ground support equipment to actually rotate and do alignment testing. I'd say at least 20% of the people in the room are safety and mission assurance, making sure everybody knows every torque, every bolt, every twist, every turn. Vibration testing. Now they're putting the optical module onto the mechanical structure of the instrument. Back in the lab near thermal vac. So that table is called Gator. It was something specially built for OCI. It's got like fractions of a degree of accuracy in terms of rotating. And the idea is you build this so that you can characterize every piece of angular distribution of the instrument. Okay, so that was 1 year of instrument development compressed into 4.5 minutes. Hope it was worth your time to pay attention. Then last slide. Oh gosh, I guess it's not done yet. Oh no, it's starting again. All right, so this is it. There was a grand reveal party about 2 weeks ago at Goddard, and what you're looking at here is the final instrument. It doesn't look like much relative to what you saw now because it's covered in foil, but this is our final view of the baby here, and you can actually see how big it is. On that table, it's taller than I am, and for those of you who have a riding tractor lawnmower, it's roughly that size. So, okay, um, I'm going to hand it back over. That's what's going on with the mission. I'm easy to find. Holler with questions.
Thanks so much, Jeremy. Yeah, those are great videos. Appreciate you walking us through all of that. So now we'll get into the second half of our telecon and hear from our three PACE Science and Applications team members. So we'll start with Emmanuel Boss, Radiative Products for the PACE era. So Emmanuel, take it away.
Good afternoon, everybody. I assume, Natasha, you have the slides to change. Is that
Yes.
correct? Good.
Yep.
So you can skip to the next slide, please. So what I'll talk to you a little bit about is the project that Robert Froid and I are doing for PACE, and it has to do with light. The ocean color, as you know, is to a large degree a function of both the optical properties of the water and the light that's impinging on the water, and that light is also important for many processes in the ocean. So our objective for PACE was to provide legacy radiative products, so continue the line of products that were available for previous mission, as well as provide novel radiative product that are useful, state-of-the-art, validated, and with known uncertainties on a pixel-by-pixel basis. Useful, that was based on inputs from a likely user. We ran among the team a survey, but yeah, useful is also for whatever users are online right now that may have feedback on things that they don't necessarily see in what I present and they would like to see as a PACE product. So by all means, please reach out to us. So the deliverable, for those who know the jargon, have to do with downwelling irradiance, scalar irradiance, and albedo, both above the surface, below the surface, spectral as well as band integrated into PAR, and UVA fluxes. And also means provide the users means to propagate the radiation subsurface to whatever depth of interest or integrated over, for example, the mix layer. Next slide, please. So why do we care about radiative products? It's the light available for algal growth, which are the base of the food chain, so things like primary production. UV exposure is critical both for life as well as for photochemistry in the upper ocean. And heat transfer, the warming of the water depends on radiation as one of the major products that modulates it. Next slide, please. So who may care about radiated products? If you're a farmer growing algae, you want to know what's available in terms of growth irradiance. UV exposure for everything from skin cancer prevention to its effect on chemical, as I said before. Fisheries scientists are very interested in primary productivity, as that's one of the major forcing for where fish are distributed along the ocean. And other researcher that might be interested in how the ocean is changing in time, either as it's warming more, so the heating part of it, as well as its effect on primary productivity and the ecosystem. Next slide, please. So what do we think we can do to improve in terms of product compared to what was available from previous and current satellites? We think that we can provide radiative products that are a better fit. For example, the current product of downwelling PAR is not really what phytoplankton are assimilating. They're simulating scalar PAR under the surface as opposed to above the surface, which is what we currently provide. So we think that just that in itself would provide a more fit parameter. Now, the problem is that we don't necessarily have the sensors to test those. The other thing is we think we can do is we can improve on classical algorithm, because now there's much more data to validate the algorithm with, and that spans much more of the globe. And indeed, recently, as I'll show you in a second, we found that there are some bias in current products. Next slide, please. So here is an example of what Robert has done for a different mission called EPIC, which is on a satellite sitting right at the Lagrange point between the moon and the Earth. And it's just in ways of showing you what we're able to do as product. He was able to derive this scalar product I told you about, also just below the surface as opposed to above the surface, as well as PAR integrated. And these are the distribution. What's nice with EPIC is EPIC sees only the latent part of the Earth the whole time. It doesn't go through. It sees it images the Earth from always the latent part because of its special. And so with time, it's able to fill up any gaps that are there. And as you can see, both in terms of coverage and details, it looks very promising. He's also had done some validation, and it looks very, I mean, with uncertainties that are as small as you hope them to be. Next slide, please. So this is the work that Charlotte is doing in my lab, using a whole bunch of radiometer deployed on profiling floats in the ocean. There's hundreds of them right now. She was able to show a variety of things. If you look at the right-hand side, she's comparing how light is attenuated as function of depth as measured by the float to what is estimated from current algorithm. And you can see that there's a significant, this is the ratio. So 1 is where you'd want to be if you have a very good algorithm. And what she looked at 3 available algorithm, and all of them were found to various degrees biased at low values. The reason for it, you can see in the lower right-hand side, is that the distribution of KD values in the ocean are lower than what has been used to train the algorithms that are currently used. And therefore, they were not trained with a lot of very clear water data, which is a large part of the ocean. That's where exactly we're seeing these bias. Also, the distributions in those databases tend to be uniform as opposed to close to log normal, as we see the distribution in the measurements of the floats. So we think that not only can we improve by using those data, we can also apply them to generate new products that are less biased, meaning they're providing a similar uncertainty in all values of attenuations in the ocean. Next slide, please. So where can you help us? If there's a need that we are not aware of, that you don't see in what we propose for PACE, we'll be more than happy to tailor a ready product for a different application, a novel one. And also, if you have a site where you can install radiometers and make radiation measurements, we're very much interested in getting as much data as possible to validate what it is we're producing. Thank you very much.
Thank you, Emmanuel. Thank you very much. I think there was a question in the chat, but if you don't mind answering it in the chat, that would be great. We can keep moving so that we don't run over, but thank you so much for your presentation. So next, I'd like to invite Darius Stromsky to tell us about next generation algorithms based on PACE capabilities to obtain inherent optical properties of seawater associated with phytoplankton, non-algal particles, and colored dissolved organic matter. So Darius, take it away, and I'll drive the slides for you.
Thank you. Okay, so our PACE project aims at developing algorithms for deriving seawater optical properties from measurements with PACE OCI instrument. Rick Reynolds is co-investigator on our projects, and we collaborate with a French team of investigators led by Hubert Loisel, and we are also involved in early adopter partnership with Veronica Lance and her team at NOAA. Next slide, please. So our algorithm is going to take OCI product of ocean remote sensing reflectance as input, and we aim at deriving 10 optical products, all hyperspectral, including attenuation coefficients for downwelling irradiance, KD, which was also described a moment ago by Emmanuel. So this will be also a product of our algorithm. And then we also will produce 9 different inherent optical properties that include backscattering and absorption properties that depend solely on seawater medium. And among these inherent optical properties, I would like to highlight today 3 of them, more specifically constituent-specific absorption coefficients associated with phytoplankton absorption, non-algal particulate absorption, and color dissolved organic matter. And emphasis on these 3 constituent coefficients is important because historically it was very difficult and challenging to derive these component absorption coefficients from inverse optical models, including ocean color models. So, and yet these coefficients have strong potential to advance ocean color science and applications, and that's why important emphasis in our project is on deriving these constituent absorption coefficients. Next slide, please. So this is a little bit technical slide, but relatively simple. So it shows what we are after, what we are trying to do. You can see the upper curve is sort of a typical total absorption coefficient spectrum of seawater. And this is what will be derived first in our algorithm. And then the challenge for us is to split or partition this total absorption coefficients in these different constituents, phytoplankton, non-algal particulate, and sedum constituents, knowing pure water absorption, which is fairly well known and relatively constant in the ocean. So what you see here, you see sort of a generic spectral shapes of these different constituents. Absorption of pure water has minimum in the blue, and rises towards longer wavelengths. And AG and AD spectra generally decrease, the magnitude decreases with wavelength, and the most complex spectral shape is associated with phytoplankton component that is generally characterized by main features include two maxima, blue and red, and minimum in twin. But the really challenge here is that AG, AD, and APH, all these components are highly variable across diverse oceanic environments. So the challenge is really to partition the total absorption, which we rely first into these variable components. Next slide, please. So without going into details, our algorithm technically will consist of multi-step derivation of these different products. In the first step, we derive KD, attenuation for irradiance, and total absorption and backscattering coefficients. And then in step 2 and 3, we use absorption partitioning models that derive these different constituent-specific absorption coefficients. And I'd like to focus a little bit on these two partitioning models because they form really the important core of our algorithm and promise significant advancements. So next slide, please. So the first absorption partitioning model will take the total absorption coefficients, which we derive in the first step of our algorithm, and partition into phytoplankton and non-algal particles plus CDOM. So that's the sum of these two components. The challenge here is that desired absorption coefficients, phytoplankton and ADG, which is all non-phytoplankton components, are highly variable in both magnitude and spectral shape, which you can see here in this graph showing numerous measurements, field measurements. So on the left-hand side, you see the spectra of phytoplankton absorption. For the sake of this illustration, they were normalized at 400 nanometers, so we can see quite dramatic variations in spectral shapes, but what's not shown explicitly is also a large variability in magnitudes of these spectra. On the right-hand side, you see the non-phytoplankton absorption spectra, so the sum of non-algal particles and CDOM. In this case, you see variability both in magnitude and spectral shapes. So especially if you look more closely, inspect these curves, they do not only differ in terms of magnitude, but also in terms of spectral shapes, something like slope, for example, or some small features. So our goal is to have a model that will utilize only weakly restrictive or no assumptions about these spectral shapes of these two desired absorption coefficients, which is a challenge, but also if successful in our development, then it will provide a significant advancement to ocean color science applications. And next, please. So the second absorption partitioning model will take the ADG, which is derived by the first absorption partitioning model, and will further partition this absorption coefficient into non-algal particles and CDOM. Once again, main challenges are that these two coefficients exhibit large variability in magnitude and spectral shapes, but additional challenges that the spectral shapes of these two components are quite similar in the sense that absorption magnitude gradually decreases with increasing wavelength in both cases. Although, the slopes, features can differ between them. So this historically has been a very big problem and challenge. We have not produced these constituent absorption coefficients routinely from ocean color missions, but we hope to achieve this goal with PACE OCI mission or PACE mission in general. So again, in this partitioning model, our goal and our ambition is to develop a scheme that will utilize only weakly restrictive assumptions about these output absorption coefficients, but at the same time, the model will be capable to discriminate between these coefficients. Next slide, please. So couple of last slides. So our development of these algorithms is well advanced. We are the basics formulations have been developed, and we are testing, still validating these algorithms. But my two last slides will be devoted to significance and example applications of optical data products from our algorithms. The first product, attenuation coefficients of downlining irradiance, KD, this has been already addressed by Emmanuel as part of Emmanuel's and Robert project, but we'll also derive it. So as Emmanuel mentioned, has multiple important values. This data product, it characterizes penetration of solar radiation through the water column. So it can also lead to derivation of irradiance at different depth levels, which are important for photochemical processes, including photosynthesis and solar heating. Now, with regard to constituent-specific inherent optical properties, they are important to ocean biology, ecology. For example, phytoplankton absorption spectrum carries information about the composition of phytoplankton pigments and composition of phytoplankton and community structures. So our data product can be used further to infer information about phytoplankton community composition, predominance of species, and so on and so forth. These inherent optical properties are also important for ocean biogeochemical constituents, such as concentrations of particulate and dissolved carbon reservoirs. And last but not least, we believe that these constituent optical products, optical coefficients, can advance characterization of water quality beyond traditional proxies of turbidity, which is essentially some crude measure of light scattering by water. So these hyperspectral constituent IOPs will provide means to characterize water quality in terms of dominance of different types of particles, such as different types of sediment particles, phytoplankton species, including species forming hormone blooms or dissolved organic matter. And the last slide, please. So this slide is sort of a conceptual illustration of how we can envision advances provided or offered by derivation or retrievals of these constituent optical products from ocean color remote sensing. As we know, ocean color spectrum is driven to first order by the ratio of backscattering to absorption coefficients. So in the numerator, we have these backscattering constituent optical properties, and the denominator we have absorption coefficients. So we will derive them all. So if we, for example, have images, ocean color images dominated by CDOM, like in the upper left-hand corner, this ocean color spectrum will be dominated by AG constituents. It's in dominator. And we have a few other examples of images or pictures of waters dominated by non-algal particles or sediment-like particles that are discharged by rivers into the coastal ocean, like in the bottom graphs in the Gulf of Mexico and Imperial Beach of Southern California, or in the upper graph also terrestrial inputs plus resuspension of the bottom. So in these cases, we expect that the water quality or ocean color spectrum will be driven mostly by non-algal particulate absorption and particulate backscattering. But in these different cases, particulate types will be different. And this information will be embedded in the data products that we will derive in the spectra of AD or BBP. And finally, on the right-hand side, we see three pictures of phytoplankton blooms associated with different species. Coccolithophores in the top, we see the whitish turquoise type of color of the ocean. Then in the middle, cyanobacterial bloom of microcystis, and then at the bottom, red tide bloom formed by Lingulodinium species. In all three cases, ocean color is essentially dominated by phytoplankton absorption spectra and backscattering, but you can see dramatic differences in this ocean color in these cases. And again, once again, this information will be embedded in spectra of optical products that we will provide. So we hope that our products will provide a basis for advancing these type of applications and interpretation of ocean color in terms of seawater composition in greater detail. Thank you very much.
Thank you very much, Darius. Very much appreciate your presentation. If there are any questions for Darius, please put them in the chat. And if you'd be so kind, Darius, to just check and engage there. But thank you. So our last presenter of the day is Pengwing Zhai. theoretical support for developing the PACE atmospheric correction algorithm, radiative transfer, and polarimetric retrieval of aerosol properties. So Peng, take it away and I'll drive for you.
Thank you. My name is Peng Zhai, and I'm the PI of this project. And my co-I is Yang Hu from NASA Langley Research Center. As you can read from the title, that this project is has two main aspects. One is to provide a radiative transfer model support for the project. Another one is we are interested in doing retrieval of aerosol and ocean color properties from multi-angle parameter data set. Next, please. I put it here, these three instrument characteristics as an introduction to the main purpose of the project. I believe in this group, everybody knows what PACE is and what the instruments are. Basically, one important aspect of this project is to build a radiative transfer model which accurately account for the instrumental characteristics, so that we can build a theoretical simulator to mimic the behavior of all three instruments given flexible atmosphere and ocean properties. Next, please. Part one, forward model part, I propose to build a radiative transfer simulator and other radiative transfer tools for the PACE project team to use, facilitate the level 1 to level 2 retrieval algorithms. The forward model is based on a monochromatic multiple scattering radiative transfer model. It accurately accounts for atmosphere-ocean coupling, polarization, and the atmosphere and ocean properties are flexible, and also for the polar regions where the solar zenith angle and viewing zenith angle is large. So we have to account for the spherical effects accurately. Also, the model include atmospheric gas absorption, including water vapor, CO2, oxygen, CH4. This use Python line absorption parameters, and I use ARTS, which is a tool to reading the Python absorption parameters and calculate the absorption cross sections. And for ozone and NO2, I also use a number of reference data set to calculate the absorption coefficients, so I can accurately calculate the interaction between gas absorption and scatterings from molecules, aerosol, and clouds. For the wavelength range and the instrument line shape functions, it's flexible. Currently, all three instruments are built in so that we can simulate their behaviors under different atmosphere and ocean properties. We also include the inelastic scattering of ocean waters, including Raman scattering and fluorescence from CDOM and phytoplankton. Next, please. Yeah, I'm showing here, we published a paper recently describe the theoretical details of this radiative transfer simulator. If you are interested in, you can Google and find this paper in Frontiers in Remote Sensing. Next. Here is one example of how to use the radiative transfer simulator. So water absorption is quite well known in the visible, but in the UV, it's still a concern. The uncertainty is still quite large from the measurement point of view. So here I'm showing the absorption coefficient of pure water there are three data sets. MCF, it's by Mason Cohn Fry, published in 2016, which is way lower than other two data sets, LEE and IOC. The IOC protocol, it's a in 2018, but IOC did not consider the 2016 MCF dataset. This model is based on retrieval. That's why some people are concerned about that dataset. It's not based on measurement purely. But just to put it here, I'm not here trying to convince you which one is better, just to tell you the uncertainty in the UV is still quite large. And I used the radiative transfer simulator to study the impact of this uncertainty to the TOA measurement. Next, please. So you can see for chlorophyll equal to 0.03 milligram per cubic meter, the total reflectance at TOA using different pure water absorption dataset. And there are two, for this data set, you can see we used two different CDUM absorption parameterization. One is MG 2009, one is MAG 2007. So 2 times 3, you have 6 cases. And on the right-hand side, you can see the relative difference of this reflectance in comparison with MCF. So MCF represents the lowest water absorption case. You can see how much they change with respect to MCF. You can think the right-hand side, the percentage difference as the uncertainty of the total reflectance due to uncertainty of water measurement, water absorption measurement, which is quite significant if you can see in the UV. Next. Here is another paper we recently published regarding a improved algorithm to treat the spherical shell effect of the Earth's atmosphere. Next, please. To illustrate what it does is that for the polar region, the spherical shell effect of the atmosphere is not negligible. It's quite significant, actually. Previously in the literature, there is a method called the pseudo-spherical shell method, which treats the attenuation of a solar beam exactly along the nadir view. In my left figure, you can see that's the direction from O to Z, the nadir view. But when we making an observation on satellite, we often see an oblique view, which is in the figure you can see from A to B. And the solar attenuation has to be from TOA to this line. This is not considered in the pseudo-spherical shell approximation. So in this new algorithm, we treat this exactly. We call that method called IPSS, improved pseudo-spherical shell method. We treat the single scattering exactly, and we also partially account for the multiple scattering effect of the spherical shell by performing the multiple to single scattering ratio in the plane parallel and apply that to the spherical shell cases. This method turned out to be very accurate. If you look at the middle figure and the right figure, for two different solar zenith angles, the pseudo-spherical shell arrow, it's a function of the viewing zenith angle, which go up to 15%. So if we use this improved spherical shell correction, the arrow is at most 0.5%. And if for the smaller solar zenith angle, it's even within 0.2%. And it's not an obvious function of the viewing angles. That's some of the feature of this new correction method. Next. This covers part 2 of this research project. Part 2 is an inverse model. Basically, we are developing retrieval algorithms from the polarimeter data. Here, it's an example of how do we explore the different remote sensing algorithm. We basically retrieve aerosol properties, including size distribution and the microphysical refractive index of different modes of aerosol. And we use that to calculate the aerosol or atmosphere path readings and remove that from the sensor measurement to get water leaving readings, which is basically an atmospheric correction algorithm using co-located polarimeter and hyperspectral radiometer data. Next. I skipped this one, talking about the details of the how does it works. Next, please. Here it shows the example of how it works. We call this new algorithm called POLIAC, which we use the polarimeter retrieve the aerosol property and apply to the spectral data. We use specs data as a proxy of the spectrometer data and use the RSP, which is a multi-angle polarimeter measurement. The aerosol information is obtained from the RSP retrieval and applied to spectrometer data to perform atmospheric correction. It shows that the atmospheric correction is doing pretty well. So next. Basically, in summary, we are providing a radiative transfer expertise to the PACE science team. And also we are doing retrieval algorithm development for aerosol microphysical properties and ocean color water leaving readings and obtain other ocean inherent optical properties. So if you folks have any comments or if you want to have collaborations in radiative transfer or remote sensing algorithms of aerosol and ocean color, please let me know. My email is in the last line. Thank you.
Thank you so much, Penguin. I very much appreciate your presentation. If there's any questions, again, feel free to put them in the chat and hopefully Penguin can answer them there. But we are at the end of our hour, a couple minutes over, so thank you all for sticking with us. Appreciate you joining, and we'll see you again. We'll see you soonest at our workshop in September. Please register, and after that, we'll let you know about our October community telecon, or we'll see you in January. So the fall is coming quickly. Thank you for joining, and we'll be in touch.
Thank you, Natasha.
Thank you.
Thank you.